Welcome, travelers, to Adventures in Security. In this video, we explore ephemeral certificates and how they are used to support zero-trust cybersecurity across microservices and user passwordless authentication. The script study guide with references is available in the video description. If you like what you see, if you learn anything, please give us a thumbs up and subscribe so you don't miss future content. Ephemeral certificates are short-lived digital credentials used to authenticate and secure communications in distributed systems without the long-term storage or reuse of private keys or certificates. They are dynamically generated and automatically expire within a short period, typically minutes or hours, significantly reducing the attack surface and potential exposure from credential compromise. These temporary certificates are particularly valuable in zero-trust architectures, cloud-native environments, and automated systems such as Kubernetes or service mesh infrastructures, where entities like microservices require secure, temporary identity without manual intervention. Ephemeral certificate use depends on protocols that typically support distributed microservices, including mTLS and SPIFFE or SPIFFE. Microservices architecture is a design paradigm in which an application consists of small, independent services that communicate with each other using lightweight protocols such as HTTP or messaging queues. Each service is responsible for a specific business capability and is developed, deployed, and scaled independently. This architectural style contrasts with monolithic systems, where all components are tightly integrated and deployed as a single unit. Microservices improve agility, scalability, and resilience, making them well-suited for dynamic, cloud-native environments. Each service can be written in a different programming language in a microservices ecosystem, maintained by a separate team, and deployed using its own lifecycle. This modularity fosters continuous delivery and integration by isolating changes to a single component rather than the entire application. Additionally, microservices promote fault isolation. If one service fails, it does not necessarily bring down the whole application, thus enhancing reliability. Their independence also allows for horizontal scaling, where only the most resource-intensive services are scaled rather than the entire application, making resource usage more efficient. Microservices are typically deployed using containers orchestrated by platforms such as Kubernetes. For instance, in a retail application, separate microservices might manage inventory, user authentication, payment processing, and order fulfillment. If the user authentication service faces high demand, it can be scaled independently without impacting other components. These services communicate through APIs or service meshes, which often include service discovery, load balancing, and mutual TLS to ensure secure and efficient interactions between components. Security and governance challenges arise in microservices due to the expanded attack surface and the necessity to manage inter-service communication securely. The National Institute of Standards and Technology, NIST, addresses such concerns in its guidance on secure microservice-based applications, NIST SP 800-0204, and its recent updates emphasize the significance of identity-based authentication, API gateway security, zero-trust integration, and the use of containers and orchestration platforms to maintain workload integrity and enforce access control. For instance, adopting SPIFFE-based workload identity with short-lived certificates enables secure service authentication without relying on static secrets. mTLS is a cryptographic protocol extension of standard TLS that facilitates bidirectional authentication between the client and server during the establishment of a secure communication channel. While traditional TLS verifies the server's identity to the client, mTLS ensures that both parties authenticate each other using X.509 certificates before initiating a secure session. This bidirectional trust model enhances security by making sure that only authenticated and authorized entities can communicate, thereby preventing impersonation, man-in-the-middle attacks, and unauthorized access within internal networks. The application of mTLS is especially critical in zero-trust environments and microservice architectures where perimeter-based security is insufficient due to the dynamic and distributed nature of workloads. In such architectures, every communication must be validated independently, and mTLS becomes a key enabler of secure service-to-service communication. When a client initiates a connection, both client and server exchange digital certificates issued by a trusted certificate authority, with each party verifying the other's certificate, ensuring both ends of the communication link are trusted and authenticated. Once the verification process is successful, an encrypted session is established, securing the integrity and confidentiality of transmitted data. A practical example of mTLS can be observed in Kubernetes clusters utilizing a service mesh like Istio. In this configuration, each microservice has a sidecar proxy, typically Envoy, that manages traffic and enforces mTLS policies. Upon startup of the service mesh control plane, for example Istio in Istio, provisions a short-lived certificate to the proxy using a trusted certificate authority, such as Citadel. When one microservice attempts to communicate with another, the proxies on both sides perform mTLS authentication. The client proxy verifies the server's certificate and vice versa, ensuring that only verified services can communicate. This mutual authentication, along with fine-grained access control policies, supports strong service identity enforcement and greatly enhances security in cloud-native environments. From a governance and compliance perspective, mTLS aligns with the principles outlined in NIST Special Publication 800-207 on Zero Trust Architecture. This publication emphasizes the need for strong authentication mechanisms and continuous validation of all entities, which mTLS inherently supports by requiring identity verification at the session level. Additionally, mTLS enables encrypted data-in-transit protections, supporting confidentiality requirements under frameworks such as NIST SP 800-53 Rev 5, which mandates secure communication protocols for federal information systems. SPIFFE is an open standard that provides a secure, scalable, and interoperable method of assigning and validating identities in distributed systems. It enables workloads, such as services, applications, and containers, to obtain strong, cryptographically verifiable identities in the form of SPIFFE IDs, which are URI-formatted strings representing the identity of a workload within a trust domain. These identities are typically backed by X.509 certificates or JWT-SVIDs, SPIFFE verifiable identity documents, which can establish trust between systems via protocols such as mTLS, without relying on long-lived secrets or manually configured credentials. SPIFFE is implemented through SPIRE, SPIFFE Runtime Environment, the control plane that issues, rotates, and revokes SPIFFE IDs and their associated credentials. SPIRE agents operate on each node and communicate with the SPIRE server to validate the workload's attributes, for example via selectors such as UID, GID, or container runtime information. Once the workload is attested, the SPIRE agent provides an X.509 SVID or JWT SVID, enabling it to communicate with other services using its identity securely. This process supports dynamic and fine-grained authentication, crucial in zero-trust and cloud-native environments where workloads can scale rapidly and unpredictably. A practical example of applying SPIFFE can be found in microservice architectures deployed with Kubernetes. In this scenario, each pod or containerized application is automatically assigned a SPIFFE ID upon startup. This ID is used to obtain a short-lived X.509 certificate from the SPIRE agent on the node. The certificate can then be used to establish authenticated mTLS connections between services. If Service A attempts to communicate with Service B, both will use their SPIFFE-issued certificates to authenticate each other, ensuring that only authorized workloads participate in inter-service communication. This process not only enforces identity-based security, but also simplifies credential management and eliminates the risk associated with static secrets or manual certificate provisioning. From a security framework standpoint, SPIFFE aligns with the principles of NIST SP 800-207 on Zero Trust architecture. It emphasizes identity-centric security by verifying workload identities for every access request and dynamically adjusting trust relationships based on the current context rather than a static network location. Additionally, SPIFFE supports NIST SP 800-53 Rev 5 compliance requirements by enabling secure authentication, credential lifecycle management, and auditability of access events. A service mesh is an infrastructure layer designed to manage and secure communication between microservices in a distributed application. It decouples communication logic from the application code by implementing this logic in Sidecar Proxies that run alongside each service instance. These proxies intercept and control all inbound and outbound traffic for the service, enabling developers to implement policies for routing, load balancing, service discovery, authentication, and observability without modifying the application code. The primary function of a service mesh is to provide secure, reliable, and observable service-to-service communication in complex environments like Kubernetes. It achieves this by managing mutual mTLS for encryption and authentication, enforcing fine-grained access policies, and offering detailed telemetry for traffic flows. Service meshes support zero trust principles by ensuring that services authenticate each other and dynamically enforcing policies based on identity and context, rather than static IP addresses or network segments. Service meshes such as Istio, Linkerd, and Consul are commonly used in modern architectures. For instance, in a Kubernetes deployment, Istio injects an Envoy proxy sidecar into each pod. When Service A communicates with Service B, the proxies handle authentication using mTLS and consult predefined policies to determine whether the communication should be allowed. These proxies also collect telemetry data and enforce retry logic, circuit breakers, and traffic splitting, all of which contribute to improved resilience and observability of the application ecosystem. NIST recognizes the importance of service meshes in securing microservice communications. In NIST Special Publication 800-204B, the guidance highlights how service meshes can be used to implement secure communication channels, integrate workload identities, and enforce security policies consistently across distributed systems. The document emphasizes that service meshes play a critical role in enabling secure DevSecOps pipelines by providing automation, visibility, and consistent policy enforcement across environments. Furthermore, service meshes are identified as key enablers of zero trust architectures by ensuring continuous authentication, authorization, and encryption within the internal network. Sidecar proxies are independent, co-deployed processes or containers that sit alongside an application or service within the same execution environment, typically within the same pod in a Kubernetes deployment. These proxies intercept and manage all network communication, entering and leaving the associated application, enabling centralized control over service discovery, load balancing, encryption, authentication, authorization, and observability. By abstracting these operational concerns into sidecar proxies, application developers can focus purely on business logic, while security and communication policies are enforced uniformly and transparently. The concept of the sidecar pattern is foundational to service mesh architectures. In this design, every microservice instance is paired with a proxy, such as Envoy, which handles all inbound and outbound traffic. This model allows for mTLS encryption between services, consistent enforcement of access control policies, collection of telemetry data for monitoring and tracing, and seamless integration with identity providers using SPIFFE or other workload identity mechanisms. Because the sidecar operates independently of the application code, it can be updated, monitored, and controlled centrally without affecting the application's logic or requiring code changes. NIST outlines the critical role of sidecar proxies in securing microservices and enforcing zero trust principles in Special Publication 800-204B. The document highlights how sidecars support workload identity, dynamic policy enforcement, and continuous authentication, essential components of secure service-to-service communication. Additionally, NIST SP 800-207 on Zero Trust Architecture recommends using identity-aware intermediaries like sidecar proxies to control and audit all access within internal networks, aligning with the concept that no communication should be inherently trusted based on network location alone. Unlike traditional public key infrastructure, PKI, certificates, which may have validity periods ranging from months to years, ephemeral certificates are issued on demand by a trusted certificate authority, CA, or an identity provider integrated into the system. These certificates are generated through secure interactions such mTLS handshakes or short-term signing mechanisms, often facilitated by protocols like SPIFFE or by service meshes such as Istio and Linkerd. Their short lifespan limits the potential damage if a certificate is leaked or compromised because the validity window is minimal. Furthermore, because the certificate is not stored long-term and is tied to a specific instance or session, it aligns with just-in-time access and least privilege principles. Ephemeral certificates enable passwordless authentication for users by replacing static credentials, such as passwords or long-lived certificates, with short-lived, cryptographically secured digital certificates that validate a user's identity for a limited duration. These certificates are issued dynamically by a trusted identity provider or certificate authority after the user has successfully authenticated through a secure, passwordless method, such as biometrics, hardware tokens, for example, FIDO2 keys, or device-based authentication, for example, smart cards or secure enclaves. Once authenticated, the identity provider generates and issues an ephemeral X.509 certificate, which the user's device uses to access systems and services through mTLS without repeatedly entering a password. The key advantage of this approach lies in its support for just-in-time identity assertions and its elimination of reusable secrets. Because ephemeral certificates have very short validity periods, often measured in minutes or hours, they reduce the risk of credential theft, phishing, and unauthorized reuse, supporting seamless integration with enterprise identity providers and authentication frameworks like SAML, OAuth 2.0, or OpenID Connect, enabling federated identity without relying on stored passwords. For example, a user accessing a cloud resource might authenticate using a biometric device, which invokes a secure identity provider to verify the user's claim. Once validated, the provider issues an ephemeral certificate, which is used to establish an mTLS session between the user's device and the target system. The server verifies the short-lived certificate's authenticity, allowing access without any password being presented or stored. This model also supports automated revocation. Since certificates expire quickly, no explicit revocation is needed in most cases, thereby simplifying lifecycle management and reducing administrative overhead. This method aligns closely with guidance provided in NIST Special Publication 800-63B, which emphasizes multi-factor and passwordless authentication as means of reducing identity-related security risks. Additionally, the use of ephemeral certificates is advocated in the context of zero-trust environments, as described in NIST SP 800-207, where continuous authentication and minimal trust assumptions are core principles. These documents underscore the importance of reducing reliance on persistent credentials and ensuring strong, dynamic user identity verification mechanisms. That's it for this video. If you have questions or comments, post those in the video discussion. And until next time, be careful what you click.